So this presentation is just going to be some basic discussion of where we are and what we might hope to achieve with the next generation of upcoming systems. I'll discuss some currently installed hardware. It'll be fairly based on sort of speeds and feeds. So which kinds of CPUs we have installed, that sort of thing. I'm not really going to be addressing things like MPI, and I'm not touching at all GPUs. Much of the discussion will be based on theoretical numbers. The industry likes to call it speeds and feeds, cores, clocks, memory, and some micro benchmarks such as stream. And I'll have some moderately interesting data from a real application benchmark, which is just Gromax using a standard package, fairly short real simulation. And then I'll get into guesses about next generation hardware. I thought I would just start with some glamour shots. This is what a so-called chip looks like today. It's actually many chips together in a single package. So in the industry, people have started not so much talking about chips, but if they mean a single slab of silicon, they'll call it a die or a chiplet. And usually they refer to this thing as a package. And this has obviously a lot of chips in it. Just for reference, this is an AMD. I'm not sure whether this is Rome, Milan, or Genoa, which recent generation. You can see it has a central die, which is actually sort of a coordinating die, but also for I/O. And then those smaller dies, the 12 smaller dies that sort of orbit it, those are the actual CPU dies. Within each of those is a multi-core die. Each has, I think, eight cores. So I'm going to be talking a lot about memory. The memory interfaces directly to that I/O die in the middle. And then it's connected to the CPU dies through a cache interface. One of the sort of interesting things about cache interfaces is that as a programmer, we think of memory as being byte addressable. But one of the fundamental organizing features of all of this level of hardware is that nothing happens on less than a cache line. So memory transfers to the I/O die are a cache line. And memory transfers between levels of cache, between the I/O die and the CPU dies, are also cache line. A cache line is canonically 64 bytes. It's something that may be useful if you're ever, well, there's a phenomenon called false sharing, which has to do with the fact that cache lines are that big. Here's an Intel. This is a Sapphire Rapids. This was actually just introduced this week. It's sort of a similar idea, but packaged quite differently. It's also using chiplets, although Intel doesn't call them that. The four things in the center are essentially the compute dies, and the four things around it are actually memory stacks. So this is a particular model of the Intel Sapphire Rapids that has onboard memory or in-package memory. So this is sort of the speeds and feeds. I've ordered it more or less chronologically. So the initial cluster installs are on that first line. So Graham, for instance, has roughly 800 nodes. We call those base nodes of the E5-2683 V4, which is a Broadwell chip, and it's 16 cores per package with 2 packages or sockets on each system. And there are some interesting things about it. One is that the base clock is only 2.2 gigahertz. Often when people who are familiar with things like laptops or maybe gamer machines, desktops, come to the server world, they're surprised that the clocks are so low. And that's really because of power. So the clocks here are 2.2 gigahertz. They can burst to 2.9 gigahertz. In a previous presentation, I actually showed a histogram of the clocks in running systems. And it's quite interesting that we often have clocks bursting to their upper range. So on those base nodes, the old base nodes, one of the interesting things I'd like to point out is that they had 40 megs of L3 cache, and the memory bandwidth seems like a lot. So that's in gigabytes per second. So 76.8 gigabytes per second seems like a lot of gigabytes per second, but you have to remember that that's divided across 16 cores. So marching down the table are sort of successive upgrades to our systems. The cluster column is not strictly true because Graham, for instance, has some Skylake and I think Cascade as well. But it is an interesting sampling of recent processors. And one of the trends you can see is that the number of cores is increasing. The clocks are going up modestly across time, especially the burst. So in the Broadwell generation, the idea of bursting server clocks was still a little bit racy or slightly outrageous to the server world, where things are sort of conservative. But people know now that even though bursting to 3.7 gigahertz, which is, over 50% boost in clock, the original complaint against that is that it would give you unpredictable runtimes, which is true, but it's also an advantage because your code will often run faster than the base clock. You can see that there's also if you squint very closely, you can see that there might be some trend towards larger L3 cache. The first 5 rows are all Intel chips, and Intel, for various reasons that I'll touch on later, has been constrained in how much L3 cache they can add. But they have gradually cranked up the memory bandwidth, which is another good thing. So, a doubling of memory bandwidth between the Broadwell and the Cascade Lake generations is really quite a major win. The bottom two are also interesting. So Narval is our most recently commissioned cluster, and its processors are AMD, and it's actually 2 generations. I put the bottom row in there just for comparison. Those are actually the nodes that host the GPUs. So it's actually a slightly newer processor hosting the GPUs. The compute nodes are 32 cores per socket. And as you can see, they have a really nice upgrade in terms of L3 cache and memory bandwidth. So I'm going to focus down on just these 4 generations of chips and talk about them in slightly more detail. This is actually not adding any detail to the previous slide. It's actually just providing some ratios. So one useful way to think of the memory bandwidth is how much memory bandwidth is provided per core. The logic is, if you're using a bunch of serial jobs sharing a single machine, you'd really like to provide as much memory bandwidth per core as possible. And if you're not careful, the serial jobs, whatever's running on the node will be starved because there isn't enough memory bandwidth to go around. But the interesting conclusion from this table is that situation has actually been improving. If you read the literature in this area, people will talk about the memory wall, and they often say, our systems are getting starved for memory bandwidth. And that's less true than you might expect, just because the manufacturers are gradually improving the memory interfaces. So in this case, I didn't show it on here, but the Broadwell generation actually has 4 memory channels per socket, and Skylake and Cascade, I believe they both have 6, and Rome has 8. So the memory interface is getting wider, and it's also going up modestly in speed. I think the Broadwell is 2.4 gigahertz, and the Cascade and Rome are probably in the range of 3.2 gigahertz, gigatransfers per second, technically speaking. Another way to look at this issue is that for every computation you do, there's probably some amount of bandwidth that you need. And that's what that last column is there. So it's bandwidth divided by some estimate of how many instructions per second you're executing. So each core can execute a certain number of instructions per cycle. and then each cycle is the clock frequency. So you see in this case, the bandwidth is actually pretty respectable for the Intel chips, and certainly competitive for Rome. And I'm definitely not trying to be down on AMD, because as you'll see later on, they have some pretty impressive systems coming. This is just a little bit more detailed. This adds a couple comments about the core process and also the power dissipation. The core process is not something we have any control over, of course, but it does explain what's happening with Intel versus AMD. The total power dissipation has increased over time, and it used to be thought that 120 watts per cycle was a lot, but as you can see, as I'll mention later on, that seems to be a place where systems are radically increasing. So the core process is this is usually given in nanometers. This describes how fine the transistors are. It's actually a L1 effective. It's a particular dimension of the transistors on the chip, and it's sort of a nominal number nowadays. It doesn't directly correspond with that. So the difference between a 14 nanometer process that Intel's been on for the past 5 years and a 7 nanometer process that Rome is on now is not actually a 2-to-1 improvement in scaling. And it's useful to point out that the essence of Moore's law, which you've probably heard of, is basically when you scale the dimensions of your transistors, like here, in some sense, the transistor has gone from 14 nanometers to 7. That happens in 2 dimensions. So instead of getting twice as many transistors, you're actually getting 4 times as many. So these are some micro benchmarks that correspond with those systems. I'm quoting theoretical memory bandwidth, which is basically just the number of channels times the width of the memory channel times the gigatransfers per second as specified by the vendor. So you can look up the specs for a Broadwell, for instance, and say the Broadwell has, I forget what it is, 4 channels. Every memory channel is 64 bits or 8 bytes wide. And the gigatransfers per second is, I forget what this is, 2.4 gigahertz, something like that. So it gives you sort of a peak theoretical bandwidth, which will never be achieved, but is still an interesting way to compare systems. I didn't do it on here, but one traditional way to compare the memory bandwidth of chips is actually to take a real measure like stream triad. Stream triad is a micro benchmark. It's actually measuring how fast a dense vector operation can take place. So the vector operation is DAXP, and it's really the core of traditional, matrix multiplication algorithms. So stream triad is an interesting, sort of realistic, but also sort of micro benchmark oriented measure. And you can calculate the efficiency of the memory interface in some sense by the ratio of the theoretical bandwidth to the stream triad. In this case, the ratio isn't that significant, and I should say it's a little bit confusing here because the theoretical numbers here are actually listed per socket, and the other ones are listed per system. But I guess the good thing is really that that even though stream triad is doing real work and generates more memory traffic than is given credit for, it's still achieving roughly half the peak theoretical memory bandwidth. That's actually sort of typical in the industry. I guess the other take home from this is that the theoretical bandwidth for core has gradually been increasing. So people are worried about the memory wall and they're actually compensating for it. The other is that the ROM generation is a big jump. The difference in time there is still only about a year, but it's a big jump. It's a 50% jump from Cascade Lake to ROM. Thrash is another micro benchmark that I like to use just because it's so simple. It's actually simpler than Triad because Thrash is just doing memset on large chunks of memory. So it's just filling memory with some constant value. So in some sense, it's a peak achievable with a loop coded in C. So it's not really doing any math, it's just filling memory, but as a memory bandwidth, as a memory benchmark goes, it's actually pretty interesting. It's also only running one thread at a time. So in this case, the thrash number is a little better than the theoretical bandwidth per core, which is really telling you that there's some benefit to the fact that the benchmarks are run on a dual socket machine, whereas the theoretical core is normalizing for the number of cores. So Triad per core is sort of the same thing. It doesn't show as much benefit as Thrash does on ROM, and that's actually not a problem because Triad is more realistic than most applications. There are probably some applications that are primarily doing really basic memory moves, so their workload resembles memset. But most cases you're doing a computation, and Triad sort of resembles the inner loop of a matrix multiply. So I would say that that last column is actually the most reasonable. And really all it's showing is that there's a gradual modest improvement. I'm going to jump straight into the application benchmark. This is just a very simple benchmark from Gromax. It's a standard bench mem. I won't describe what it does in Gromax. It's a condensed matter simulation, I suppose. I ran it on single whole nodes of various generations on various clusters. And I ran it on between 1 and the number of available CPUs on that node. So this is not attempting to do anything with MPI. So in that sense, it's not like every program we run. And the main complaint about this is just it's running, for instance, when it runs one core, it's running that one core alone with nothing else occupying the other cores. So various resources that are on the chip that are shared between cores are not being shared in this case, whereas on a system where you're sharing a node with multiple other applications or jobs, you would expect that competition. So it's overestimating the performance for low thread counts. This is just, it's sort of eye candy in the sense that it just shows the kind, so this is, so I should say, this is the Gromax test. It's run on a single node. On the x-axis is the number of cores, and elapsed time is the thing that we're measuring here. So there are a couple take-homes. One is that you really like to see that exponential decay. That means that it's scaling. I think it's good for everyone to run their application in a scaling like this, maybe not starting at 1 and going to the max number of cores, but at least sampling a few points along the line, because it's a great sanity check. So in this case, you know, applications start at about 1,000 seconds and immediately go down to roughly half that. I think for instance, the blue Skylake, I believe, is starting at about 1,000 and drops to 500. And that's great. You know, so certainly running it on 2 cores is a guaranteed good thing. But you'll notice that after 500, it doesn't go to 250. Or it's a little above 250 for 4 cores, for instance. So this kind of graph looks very flat on the right, which is a little bit deceptive because this particular application scales pretty well. But it looks sort of flat just because the numbers are low. Maybe I should have log scaled the y-axis to emphasize that. Another thing I like to point out about this is that there are bumps in this. So for instance, if you look at Rome, which is the yellow, you'll see there's a bump at about 15 or 16 cores. And that is probably an interaction between how Gromax divides its work among cores and how the cores on the node are laid out. This is an AMD, so it's got chiplets. All the other systems, the Intel systems, are all single chip cores, single chip sockets. So there's less of an effect when you involve two sockets. Gromax has some peculiarities in how it balances load among the domain that it's trying to simulate, which is why, for instance, there are missing points between 20 and 25. This is another way to look at the same data. These are exactly the same runs, but instead of plotting elapsed time as a function of cores, I'm actually plotting the amount of core seconds, or basically compute resources, consumed by each number of cores. So in other words, the task is fixed, and all we're doing here is giving it more cores to work with. Actually, let me go back here. One thing I liked about this graph is that it turned out in the order that I was expecting. That is, these lines are ordered in terms of purchase time, basically, or advancedness of the chip. So, Broadwell is the slowest, and Cascade, which came a year or two after that, is the next fastest. Actually, that's not true. Skylake is next. But the very latest generation, Rome and Milan, are substantially faster than Broadwell, which is a nice thing to see. Here, Broadwell is really an outlier. So it's interesting that all of these lines are slanted upwards, which is just saying that as you use more cores, your elapsed time may improve, but your overall resource consumption is also increasing. It's not increasing terribly. So especially in the area under 10, for instance, you might cry a little bit because between 1 and 2 cores you used more resources, but it's fairly flat. Terrible things are not happening. You can't really say that about the Broadwell. The right-hand side of the Broadwell, which is 32 cores, is using substantially more resources than 1 or 2 cores. And I think that's important to note. People should know their application and how it scales when viewed in this way, because if you view it in this way, everything looks good, right? There's a gradual trend downward. Elapsed time is decreasing as you add more resources. That's fine. But if you view it this way, which is a fixed amount of time, how much resource is it consuming? It's sort of a very different picture. And I really like this picture. You also see an effect over on the right side, which is only present on the 64 core nodes on Narval. And I'm not really sure why that increases so badly. The topology of the narwhal nodes is probably just not well understood by Gromax. But most applications will, all applications will have this sort of upward trend in their scaling. And really the message with respect to today's talk is just that there has been an improvement. So the very latest machine here is more or less at the bottom, and the old stuff is at the top. I guess this also says that, we're certainly going to be getting rid of all of the Broadwell machines in the next year. And that's not a bad thing, because they are substantially slower. So the current clusters were commissioned quite a while ago. Those Broadwell nodes are about 6 years old. They're out of warranty. They're also, in some cases, from vendors that we want to be rid of. So there's really, replacing them is going to be a major win for us. those nodes in the middle, the Skylake and Cascade Lake, and there are some others, by the way, those are upgrades relative to the 6-year-old Broadwells. And I think it's really encouraging to look at how much things have changed, and then a few of the properties of upcoming systems that make me very enthusiastic about how they'll change in the future. I just mentioned that architecting these systems is very much a dilemma because CPUs and GPUs, any given workload will use one or the other. And you can't get rid of CPU if you're GPU oriented, but if you're CPU oriented, any money spent on GPUs is not helping you. And GPUs can be very expensive. We were just talking about sort of rough ideas of system costs the other day. And you could easily spend, for a single node, you could easily spend $100,000 on GPUs, whereas on CPUs, it's more like $10,000 or $20,000 for an entire node. And memory doesn't really even add up to that. Another thing which I think is interesting, but I won't really be, well, I'll be touching on a little bit, is that we have a similar dichotomous situation between users whose workloads are compact, meaning they use very little memory, and workloads that are very memory intensive. And this interacts to some degree with the CPU and GPU dichotomy. But memory intensive tends to be just a couple different types of workloads. Some workloads put data in memory essentially as a fast file cache, because they're assuming that they can't read for instance, AI training data sets are normally stored in DRAM, even though they're being processed by the GPU based on the assumption that it would be too slow to read them from disk. In some cases that's true, and in some cases it's not. That kind of memory intensiveness is very different from the memory intensiveness of someone who is really filling data with, filling memory with data that is computed with directly. So for instance, some material simulations are data bound. A lot of chemistry programs, especially quantum chemistry, often has a very high memory footprint. It's interesting that there are these very distinct groups of usage within our community, and it has an effect on the sorts of hardware that we'd like to buy. So I think I mentioned most of these things before. Intel has been stuck. They made some bad strategic changes about how they run their fabs that kept them stuck at 14 nanometers for a long time. So they've just made relatively small tweaks. So slightly more cores, slightly more memory clock, a little bit of improvement in instruction sets such as AVX 512, small improvements in the performance of their transistors that give them a slightly better power performance. These are all good things, but they're not the kind of sort of bold Moore's law-like changes that we've come to expect. And AMD took a big risk in that it reinvented itself. It was doing very poorly, but it decided to go with chiplets as sort of an organizing feature of its architecture. And as you can see from Narval, from Milan and Rome, that's really paid off well. With chiplets, I mean, chiplets are something that Intel can avail themselves of too, but it just takes time for them to become part of their product line. So AMD has been consuming 7 and 5 nanometer fab capacity. TSMC is the world's largest chip maker. They do an amazing job because they focus so much on being able to churn out these chips and to advance them year after year. And that's something where Intel has had trouble. So even Intel's most advanced process, maybe before yesterday, I'm not sure, was their 10 nanometer so-called superfin, which is something that basically they were producing 3 or 4 years ago as well. So they used to have a reputation for advancing, at least once a year, a sort of a tick-tock cadence where they would improve their fabs on roughly a 1.5 to 2 year cycle with an in-between improvement. And that just hasn't happened. And it has, just if you're interested, it has primarily to do with the details of the fab. They bet against a lithographic technology called extreme ultraviolet because those systems were very difficult to make work. But TSMC put in that work, and now they're have a big advantage. Chiplets, there are various reasons that chiplets are a good thing. The one on the bottom is also kind of interesting because one of the themes going forward in future systems will be how much cache and how much memory are integrated into the system. So HBM stands for high bandwidth memory. It basically means a stack of DRAM that's integrated in a package. This is just sort of a joke. Intel, I think it was just yesterday, or at least earlier this week, just introduced their 4th generation Xeon, which is codenamed Sapphire Lake, and they're introducing a lot of separate chips. That's the main point of this graph, this table. They're not slowing down. They think they can still do well in the market, and they may. So there are a few parts of this that are really, so on here, I guess you can't probably see much, but I guess the main thing to look at here is the core count, which is this 3rd column, and you can see that it maxes out at about 56. There's actually a 60 core chip down here too. I don't really understand that, but 56 seems to be the nominal expected core count for these chips. And down here at the bottom, these green chips marked max are also very interesting because these chips have memory in package. All the rest are using chiplets, but these are using chiplets plus memory chiplets. And that's a very interesting thing for us to look at going forward, just because putting HBM memory in the package takes you to a terabyte per second of memory bandwidth. It just automatically jumps you up to a much higher realm of memory bandwidth. So this is sort of just a summary of current and almost current chips. Intel is basically up to 64 cores or 56 cores with around 100 megs of cache, which sounds like a lot, but that's 112.4 megs of cache for 56 cores. So it's really only 2 megs per core, which, if you think of it in those terms, is not all that much. I mean, our nominal process size is 4 gigs per core. So 2 megs per core means that your core ratio is 2000 to 1, which is a pretty small ratio. These are pretty hot chips. Intel is still running on a trailing fab. So they have an aggressive plan to increase the quality of their transistors, the fineness. But these 56 cores are clearly thermally limited because 350 watts dissipating from a single package is very hot. Our current systems are designed for around, I think you might recall from that previous slide, around 140 watts per socket. This is a lot more. This basically means that for a standard dual socket systems, they have to be water cooled. The other interesting thing is that the clock frequencies are not all that high. This is a place where AMD may actually have some advantage just because they're on TSMC and use finer transistors. The second bullet there is the version of the chip that has memory in package. There are a couple interesting things about it. One is that it costs about 20% more, which is not outrageous considering that it has a terabyte per second of memory bandwidth within the socket. The clocks are, depending on how you look at it, a little bit lower. The base clock is actually quite high, but the burst clock and the all cores burst clock. That's what those three numbers mean. That's the 2.7 gigahertz base clock, 3.1 gigahertz all cores burst. And then 3.5 is the subset. So if a few cores need to burst, they can reach 3.5. AMD's next generation is called Genoa. We know that it will have 96 cores in a socket with 384 gigabytes or megabytes of cache, which is really a lot of cache. I mean, it's what, about 30% more per core than Intel. The power dissipation is similar. The clocks are comparable, maybe a little bit better. At this point, it's the clock frequency is basically just a question of how much power can you dissipate. AMD has been producing chips which have a -X on them, which means that they stack extra chips in the package. Those extra chips are actually cache chips. And so the current thinking in the rumor mill online is that there will be a Genoa X, which has a gigabyte of memory in the package as in the form of cache. Now that's compared to 64 gigabytes in the Intel Max. So it's not the same thing, but it's also faster than the HBM. So for jobs that have relatively small footprints, the gigabyte of cache for 96 cores might actually be quite a sweet spot, because we actually have programs, we actually have jobs where the per core memory usage is in the range of 100 megs, and those would fit in cache on this chip. Another interesting thing to compare is that alongside Genoa will be Bergamo, which is more cores, but probably reduced L3 and definitely no X version. So AMD is describing these as designed for cloud, which is kind of peculiar because they also maximize the floating point throughput. So in some sense, they're designed for scalable HPC as well. And that'll be 128 cores per socket, which is kind of astonishing because you could easily have a single system with 256 cores, and it's just a dual socket system. So for 1,000 watts, you're getting 256 cores, which is kind of mind-blowing. The rumor mill says that the clock frequency for these is going to be comparable. They're not going to decrease the clock much. So the floating point throughput for just accepting a smaller L3, maybe a higher power, is going to be 30% more, which is really something that we need to look at. This is sort of an inside baseball slide, I guess. There seems to be consensus that we're close to getting federal approval for the upgrades in the next year. We still don't have provincial match, or at least we're not that confident of it. There will have to be a process of writing requests for proposals or something like that in order to get vendors to tell us what they're willing to sell us. In the past, that process has taken between something like 340 days to just under 2 years, which is a bit shocking. John Morton mentioned these in a staff meeting yesterday. So the chances of getting refreshed hardware this year, it would be great, but I think we probably shouldn't make any decisions based on that assumption, which has implications for the kinds of hardware we expect. Maybe things will be a little bit faster because we're not starting from scratch. We have machine rooms which will probably need some tune-ups, but we're not really starting with empty rooms. I wouldn't want to bet on whether Genoa or Sapphire Rapids will actually be delivered, just because those things arriving on loading docks is optimistically many months away. So Sapphire Rapids is probably deliverable right now, but in 8 months, in 9 months, in 12 months, there might be a new version. And Genoa, AMD is playing cards pretty close to their vest about what happens after that. Thought I would just give you some pretty pictures that describe the cores. This is a Sapphire Rapids core. I guess the thing, so if you've never looked at a chart like that or a diagram like this, the important thing is to realize that data is flowing basically from the top to the bottom. So at the top is things like instruction fetch, and you can think of the rows as being basically pipeline steps. And the width is really the take-home message here, which is how many types of operations can this core execute at the same time. And what this is saying is that various parts of this are in the range of six independent instructions or micro instructions per cycle. In some cases, there are operations that have multiple ports as well. And by contrast, this is sort of a vaguely similar diagram for AMD Zen 4, which is the Genoa generation. So the progression of data is still from top to bottom, and really the take-home message is how wide is it? So in this case, you can see that there are a very large number of parallel units on that second to the bottom row, and that represents instructions that can be executing and even completing at the same time. I just thought I'd throw in a few sort of slightly provocative questions like, does general purpose really exist? We have so many small communities that are relatively specialized that are using our systems. The GPU people don't really have that much to say to the people who are doing, for instance, condensed matter simulations that have tiny memory footprints, such as the 100 meg per core people. We have at least two separate and quite distinct communities that are very high memory use. Similarly, we've always approached the idea of MPI as being something that everyone needs. But if you have very fat nodes, such as 256 cores per node, maybe you want to de-emphasize MPI because very fast MPI friendly interconnects are expensive. So we can't do away with the interconnect entirely because we need fast file systems. But if all you wanted was a fast file system, you probably wouldn't choose InfiniBand. You might just choose 100 gigabit Ethernet. This is just a description of some of the things that will affect what kind of products we wind up with. And that's about it.